Hey everybody, and welcome back to Calc 3 Online. This is going to be our third of, I believe, 4 review videos. And to start off today, I'm just going to do a flux example. So I want to compute the flux across this kind of upside down paraboloid, right? And we just consider the field XYZ acting on the surface. So, this is really just a surface integral. Basically, the flux is just a fancy word for, like, you have this upside down paraboloid here, and we're sort of thinking of this field, like, I'm just going to say it looks like this, sort of passing across this surface, and we're just looking at the interaction between really the normal vector at a given point and the the vector of the field at that point. So it's really just found by doing double integral s f dot ds, but this is kind of like the bold s, but really think of that as f dot n ds. And the normal vector is found by doing a cross product. So, really, you can think of it as f dot r with respect to whatever parameter u you have, r with respect to v, dA. And that's really the way that I kind of do these things. So basically parameterizing things and then finding cross products, doing this dot product is how we're going to do it. So anytime I have one of these things that can be written as a z equals surface, I pretty much just parameterize it as like x equals x, y equals y, and then z equals 1 minus x squared minus y squared. And then I can basically do r with respect to x and get 1, 0, minus 2x. R with respect to y is 0, 1, these are vectors, and then minus 2y. And then, I'm going to basically do my cross product of those things. So I've got I, j, k, 1, 0, negative 2x, 0, 1, negative 2y, and you're just going to find like this determinant. So let's see, if you do that out, blank those out, you get 0 minus a minus 2x, so you get 2x, and then blank those out, minus 2y, minus 0, so just, but this one's the negative 1, so minus a minus 2y. And then last but not least, 1 minus 0, so you get 1. So that's my vector. I'm going to be putting in, in here, basically. All right, so now we can set this thing up. F parameterized, it's just the field x, y, z. So put an x in x, you get x, y in y, you get y. And then z is 1 minus x squared minus y squared. And that's what I'm going to dot with 2x, 2y, 1. And if you do that out, basically, if you dot product and simplify everything, it's going to simplify to 1 plus x squared plus y squared dA. So I just realized I meant to add one thing. I kind of drew it, but I just left it out of this. I wanted this thing to be cut off by the plane z equals 0. So I want basically exactly this picture where it's just cut off, right there. That just makes it so you can actually solve this thing, because otherwise it's like a boundless thing. But we're going to put a bound on it at z equals 0. And that's going to dictate, give me a circle down there, and that's going to help me get the bounds for this double integral. So if it is cut off at z equals 0, right, you should basically switch to polar now. So like this region like R, I'm going to integrate over. You're going to have 1 plus r squared, right, times r dr d theta. And then r is running 0 to 1. It's just like if you blank out z, right, make it a 0, you just get a unit circle right there. And then 0 to 2 pi. And then basically it's a nice integral from there. You could just multiply by 2 pi because there's no theta dependence on the inner integral. You can multiply it into r. And then it's just polynomial. Everything's kind of nice from there. So anyways, long story short, you're going to get 3 pi over 2. So that's kind of flux in a nutshell. Basically, you can think of these as just one dimension up versions of line integrals. They have an analog to, the f.dr line integral, and they also have an analog to the ds one. So you can think like how much area is there basically between a surface and, a two-dimensional region. Just like you can think about how much, it's not area, how much volume there is between a surface and a two-dimensional region down in like the plane, let's say. Just like for the ds line integrals, you can think about how much area there is between a function and the path in the plane. All right. I want to do another one of these because I think they are historically kind of tough, and they're basically good to see get worked out. So this double integral at first glance is really kind of messy, but whenever you have this like whenever you have a structure inside that's really messy, let me just back up a second, you should try to think like substitutions. And here, if you substituted it so that you could get like sine of like u over v or something, sine of u over v, du dv, is actually going to be like a nice integral because, u is constant with v and v is constant with u. So you could basically do those two integrals out really nicely. And so that's kind of a clue to me that maybe I want to try a substitution here. And so this is another one of these change of variable problems. So if you let u equal x plus 2y, v equal x minus 2y, same kind of thing as the one in a few videos ago. You want to go and get x and y solved for. So if you do this one out, I could eliminate x by subtracting and do u minus v equals 4y. So y is u minus v over 4. That's going to be helpful. And then you could get rid of y by just adding. So you could do u plus v equals 2x, and then u plus v over 2 is x. All right. We also need to plot where this thing is. So they say it's a triangle with the vertices 0, 0, 2, negative 1, and 4, 0. So if you plot that out, 0, 0, 1, 2, negative 1, and then 1, 2, 3, 4, 0. So that is my region I'm integrating over. And that's in, XY space. I want to do, all these reductions and get this thing, figured out in UV space so I can get my bounds from UV. So let's take this line. So when y equals 0, right, I get u minus v over 4 equals 0, or just u equals v, right? So that's going to be something I'll graph here in a second. And then let's take this. This line is, what would that be? Just negative a half x equals y. And so when you're on that part, right, negative a half x equals y. just plugging in, the x and the y here, you're going to have, looks kind of messy, but you'll have u, here. I'll have negative a half x, which is u plus v over 2, equals u minus v over 4. And lots of algebra there. You're going to get u equals 0. It's not horrible because you get a 4 on both sides, and simplifies out quite nice, actually. So that's going to be another thing I'll graph here in a second. And then last but not least, we got this line segment. And on that one, probably the way I would just get that equation is I just backtrack it with the slope. You're going to see that it goes through -2, right? And it's got a slope of 1/2. So it is 1/2 x minus 2 equals y. And so on 1/2 x minus 2 equals y, in terms of u and v, you're going to have x is u plus v over 2, and then y is u minus v over 4. Here, a little bit messier because you can't just cancel the 4s and stuff on the bottom because you got 2 terms, of course, over here. But it does simplify out fairly nice. You get v equals 4, which is nice. And so this gives me my my new region, right? So these 3 things I've circled here. If I plot them, right? So now I'm thinking v up here and u here, all right? One of them was u equals v, which is just that line. All right, one is v equals 4. Let's just say that's 4. V equals 4. And one of them is u equals 0. So that's just this right here. So my region that I'm integrating over is actually still a triangle, but kind of a nicer triangle, actually, if you think about it. Because here you got 2 diagonal lines that are kind of annoying to deal with. But here it's like a right triangle, which is nice, obviously. So this is going to be my new region that I have to integrate over. All right, so I just switched over here and copied over the new UV region. So what we're going to do is do a change of variables from x, y space to UV space. When we do that change of variables, right, my new bounds in u, let's say, will go 0 out to v, right, just kind of doing a type 2 region for no good reason. And then in the vertical distance, the v, it goes 0 to 4, right? And then I have sine of u over v, and I'm going to need in here a Jacobian, right? Du, let's just going to write dA for right now. So the Jacobian, right, is basically, again, this tool that measures sort of the change in area between the transformations. And you just get that by doing these partial derivatives, right? So here it's just going to be a 2 by 2 determinant. And, this first one is the partial of, let's say, x with respect to u. And so if you just go back to our x equation, we would get 1/2. And then you do partial of x with respect to v, which is also a half. Partial of y with respect to u is 1/4. Partial of y with respect to v is -1/4. And so if you do that out, that determinant is -1/4. But we put in 1/4 because it is measuring how much the area is changing. We don't really care about flipping of direction. There's really a magnitude involved in there, which you can actually see in the flux computations. When we do those, there's a magnitude involved there too. So now at this point, we can actually just go and start computing the integral. We got everything we need for it. So we're just going to solve this thing out in like the UV space. All right. So, you can pull that quarter out, and then got 0 to 4 still. And then we're going to do a du integral. And so basically 1 over v that's inside of this sign is like a constant. So we're going to have to divide out by 1 over v or multiply by v. And then, of course, take the integral of sine, you're going to get negative cosine. So you're going to get minus v cosine u over v from 0 to v dv is going to be my next integral. If you do that out, let's see, you're going to get, you can pull the v out, you're going to get cosine of 1, because v over v minus 1 dv. And then, so that's all constant, right? So I can pull that out, and so I got cosine 1 minus 1, integral 0 to 4 of, I can also pull out negative, just v dv. And so you do v squared over 2, evaluated from 0 to 4. And if you do that, you're going to get negative 2 cosine 1 minus 1, which I guess maybe it looks a little nicer this way, 2 minus 2 cosine of 1. So that's it. So those change of variable problems are super handy, and definitely recommend you kind of have those down by the end of this course. All right. So the last problem I want to do in this video is another optimization problem, but not the Lagrange multiplier one. So if we have this function, you've got these partial derivatives here, okay? And this one too. They're pretty messy. And this function has 4 critical points. And I want to calculate the critical points and indicate whether each determines a local max or a local min or a saddle point, okay? So the first thing we got to do to get the critical points, right, is to set the partials equal to 0. So, if you take this and think f of x equal to 0, basically you could get that. You're not going to get it with the e. The e, is going to be positive. But you could get it with y equals 0 or x equals negative 1. So let's just take each of those. So if x equals negative 1, then, in here, right, you'll basically get, we're setting this equal to 0, 2, just solving a system, right? You're going to get negative x, negative 1, is 1, times 2 minus 1 is 1, then you get a 2y minus 1, a 2y plus 1, and then you get the e thing, but it doesn't matter, right? So the only way that'll be 0 is if you have these two factors go into 0. So y is a half or negative a half. So one of these critical points is just going to be when x equals negative 1, y can be a half, and then also x negative 1 and y negative a half. Another case is this one, right? So when y equals 0, this will be a 1, and then that'll be a negative 1, and that'll be a 1. So you're going to get 0 equals negative x times x plus 2 times negative 1. So 0 equals x times x plus 2. So x equals 0 or negative 2. So the other critical points are 0, 0 is 1, and then 0, negative 2. Yeah. Nope. Sorry about that. That should be flipped on the last one. Should be negative 2, 0. There we go. So that's how you can get your critical points. Much easier if you already have the derivatives, right? in order to figure out this stuff, you do kind of need to just remember basically the second derivative test. So it's a little more cumbersome than the second derivative test in Calc 1 for sure. It involves this thing, capital D is what our book calls it, which is really f(x)(x) at a point minus, or sorry, not minus yet, times f with respect to y twice at the point, these are the critical points, minus the mixed partial 1 at ab squared. And so the first thing to do is calculate d. I mean, that's kind of what I do first. And if d is less than 0, it's going to actually be a saddle point. So if you take each of these points, right? Let's take 0, 0 here. If you plug in 0, 0 to these partials, right? These second order partials, right? And you solve this, you're actually going to get d is less than 0 here. And you're actually going to also get d is less than 0 here. And so those two are saddle points, right? The other ones, you get d is greater than 0. And then the idea with these problems is if, so in the other case, d is greater than 0, that's kind of like an initial check. You're good. Then what you want to do is check the second, so f with respect to x twice at like a point. So you can do like -1, 1/2. And if you do that one, you're going to notice that it is greater than 0. And so what you can kind of think of this as it's sort of like concaving up, okay? And so at that point, the point, where there's some sort of max or min, local max or min happening, it would be a minimum. So this is a local min. And then if you do the same thing for, so the last point, d is greater than 0 for that last point. And if you check the f(x)(x) at that point, -1, -1/2, you're going to see that this time it is less than 0, right? And so that implies that it is a, local max, okay? So kind of skipping some of the, algebra steps in there, but these are very important concepts too from this course. Definitely want to make sure you know how to do all this stuff too. There's a lot of work sometimes in these problems because a lot of times you're just going to be given that and you're going to be like, optimize it. And you've got to get all these partials. You've got to do all this algebra out. You got to compute this thing for all of them. And then you got to go through, and if d is greater than 0 for any of them, then you might have a max or min, and so you got to go do that. And I'm not gonna have time to do like an absolute max or min problem in here, but if you were asked to do an absolute max or min problem, you would have it on a bounded region, and so you would have to do all of this, but then you would also have to do some evaluations of the function on the border, right? And so that's another thing that we saw, and another thing that's like super important from this course that I definitely want you to know. So, a lot of stuff in this video, and that is about it for this review video.